When we think about building good software, the instinct is usually pretty simple. Make it run as fast as humanly possible. But you can build an application that responds to a single click in a lightning-fast 50 milliseconds, and watch that exact same application instantly collapse the moment 10,000 users try to click it at the exact same time. This diagram shows latency, the metric for a single request. It measures how fast one user experiences an action. But watch what happens when we introduce throughput, the system's total capacity. If the pipe isn't wide enough, everything bottlenecks and grinds to a halt. Optimizing solely for latency is like hiring a master chef who can cook a perfect meal in 2 minutes. That sounds great, until you realize the kitchen is the size of a closet. They can feed exactly 5 customers a night, while everyone else waiting outside starves. Flip the scenario, and you have a massive factory kitchen that pumps out 500 meals an hour. The total volume is huge, but each individual customer ends up waiting 40 grueling minutes in line just to get their specific plate. Raw speed for one user is an entirely different engineering challenge than scalability for many. Achieving true performance requires a completely different strategy than simply pushing processors to run faster. The most massive systems in the world don't actually achieve their scale by processing tasks faster. They survive by ruthlessly avoiding unnecessary work. This is a massive trap with modern AI-generated code. AI will happily write logic that forces your database to wake up, scan its records, and recalculate the exact same answer for every single user request that comes in. The solution is a caching layer. Caching simply stores the results of an expensive database query in temporary memory. When the next user asks the same question, the sleek front layer hands them the pre-computed answer, and the main database never lifts a finger. YouTube survives its global load by aggressively caching video metadata, thumbnails, and distributing content through global delivery networks. Their servers aren't recalculating the details of a viral video millions of times a minute. They calculate it once and hand out copies. The scale of YouTube's architecture necessitated these specific caching techniques from the very beginning. Solving that exact mathematical puzzle of scale is what made their early acquisition by Google so lucrative. Without a caching layer to intercept redundant tasks, scaling any read-heavy platform is mathematically impossible. The core rule of system design is simple: never recompute what you already know. Throwing a cache in front of a database is incredibly easy. Keeping that cache accurate is famously one of the hardest problems in computer science. When a user updates the database to a new color, the cache continues handing out the old color. A TTL adds a timer to eventually fetch the update. But until it hits 0, your system is actively lying to users. The more accurate industry standard is the cache aside strategy. The system checks the cache, finds it deliberately emptied, actively fetches fresh data from the main database, and immediately updates the cache for the next user in line. Facebook's infrastructure heavily relies on this. Their feeds, like counts, and comments are aggressively cached, so the servers don't melt under the throughput. But they require intensely complex logic to constantly invalidate and refresh that cache the very microsecond a new interaction happens. This complex background architecture, managing exactly when millions of caches update, enables a tech monolith to function at a publicly traded scale. A cache is a powerful performance hack, not a permanent source of truth. If developers blindly add caching layers without writing the logic to invalidate them, they introduce catastrophic, silent bugs right into the core of the application. Why are users so often trapped staring at a spinning loading wheel just because they clicked buy or submit? That loading wheel usually means the system is using synchronous processing. It is forcing the user's browser to completely freeze and wait while the server finishes every single cascading task in real time, saving the file, sending the receipt email, and updating the analytics dashboard. Look at the top timeline. That is asynchronous processing. The system instantly gives a success screen, so users keep clicking. Heavy secondary tasks drop to a bottom track queue, waiting until a worker process handles them. The user never notices, and the screen never freezes. When you book a ride on Uber, the interface responds instantly to lock in your map. But the complex machinery of billing your card, sending push notifications, and updating driver analytics are entirely asynchronous background jobs. Relying heavily on that asynchronous architecture is exactly how platforms process high-stakes, real-time logistics without buckling under the weight of millions of active writers. The definitive rule here is simple. If the user does not actually need the result of a process to continue their immediate journey, offload it. Blocking the user to do background math is always a failure of design. Achieving the ultimate tier of efficiency means hitting the Google search standard, where milliseconds of latency somehow coexist perfectly with millions of simultaneous queries. That impossible balance is never achieved just by making processors run hotter or desperately throwing hundreds of expensive servers at a bottleneck. So before you write your next block of code or ask an AI to generate an entire backend, go down the checklist. Ask if the operation is actually latency sensitive. Ask if you can cache the data, and exactly when that cache will go stale. Ask if the user truly needs to wait for this process right now. True professional performance has very little to do with raw speed. It is built entirely on the relentless avoidance of unnecessary work.